All right, let's talk about the nuclear magnetron. You electrical engineers out there, you're going to go, what? Use an isotope in a magnetron? You're going to say, that won't work. There's no return ground on it. You physics engineers are going to go, oh no, that's not going to work. The isotope goes in all directions. Actually, a nuclear magnetron has been built by our government and by some individuals of government several times. Okay. You can't use them in radar systems because of how they react. But as far as converting particles into wave energy, yeah, they do work. And they pretty much work exactly the same way as a normal magnetron, except instead of having a hot cathode that boils off electrons, they have a cold cathode that boils off electrons. You can use, and in fact, you can use positive particles also. You don't have to use negative particles. Positive particles produce just as much energy as what negative particles do. Is a nuclear magnetron different? Yes, it is different. It's quite different. You need down here, if you look at the bottom left-hand corner of the picture, you see this thing called a spark gap. And you need a spark gap in a nuclear magnetron because the particles eventually fall back to the cold cathode here, and it builds up voltage and an electrostatic field voltage, and at some point it'll arc from the isotope over to what is normally known as an anode. You don't really have an anode as such in a nuclear magnetron because it really doesn't have a voltage on it. The particles are converted in the same manner that they're converted into wave energy in a regular magnetron. So why use a nuclear magnetron? That's, everybody goes, well, why do you want a nuclear magnetron? Well, the fact is that isotopes are high voltage, most of them, and high voltage particles have a lot of energy, and the only way you can capture high energy is with a device like a magnetron. The magnetron actually converts, it can go up into the 100,000 or million volt range of particles and still convert the particle energy into useful wave energy that can be converted then back to regular, normal electronic energies. In other words, things that can run DC motors, things that can run computers and that kind of stuff. But trying to get a 100,000 volt or million volt particle to convert that to something that electronics can use, that's very, very difficult. And I know you physics people out there are going to go, oh, but you can't build the cathode to have enough surface area to produce power. That is just not the case. They've proven time and time again with actually building them that they produce tremendous amounts of power. So from this point of view, the nuclear magnetron was the ideal device to use because it actually has high efficiencies. But this is just an introduction to what it can do. I'm going to do a complete video that you can look on this website, and I'll go into the ins and outs of a nuclear magnetron and what other stuff has to be in it and how it works and all that kind of stuff. This is just a preliminary information about that it does work, it has been built. So we're going to talk about the efficiencies. All right, we're going to talk about the efficiency of the nuclear magnetron. So there's some papers out there that was done by a prestigious college that said the nuclear magnetron would only be 3% efficient. The government nuclear people said it would be 80% efficient. So what's the real answer? The real answer is it's about 68% efficient in energy conversion. This is the amount of electrons that actually go into the rotational field that are emitted by the isotope, and that. There's a lot of extremely complicated things that involve a nuclear magnetron system, and you have to take a lot of different things into consideration about how it's designed and all the other things. But the basic answer is the efficiency can be very, very good compared to a nuclear power plant. Weight, size, and everything. This is the lightest weight nuclear device on the planet. You can take multiple devices and tie them together and convert the energy back into an electrical system, and we're going to cover the cyclotron wave converter next. This is a cyclotron wave converter. This is what it looks like. This is what it looks like. The input port takes the microwave energy from the nuclear magnetron and converts it back to a DC output here at this end on the right side that a normal electrical device can use. Now you're going to think to yourself, well, we've got this huge nuclear plant with steam turbines and cooling ponds and that. The efficiency of these devices, of this cyclotron wave converter, the efficiency of these devices are so high that cooling really isn't much of a problem. Do you need some cooling? Yes, you do. Do you need a giant lake pond? No. You can, normal airflow going past these things is pretty much all you need to cool these devices. The efficiencies are just so high in these devices compared to other compared to the rest of the nuclear things that you can't really compare the two, because nuclear normally means heat something up, boil steam, run it through a turbine a turbine that drives a generator, and then you get electric out of the thing. And these, when you're talking about this, it's completely different technology and how it works. So there's no way really to relate it almost. It's a high efficiency electrical device is the best way to describe this. And you say, well, it's got to be heavy. A 50,000 watt device is only about 3 feet long and weighs about 10 pounds in a 50,000 watt device. You can't, a 50,000 watt generator is probably 100 times that weight. You can't, that's why you can't even compare these technologies. The weight of one of these converters, converting the microwave back to electricity, it's just, you can't even compare it because of the weights and the efficiencies involved. So this is why we use a cyclotron wave converter, is because of its lightweight and its efficiency with the nuclear powered magnetron that produces microwaves. Between the two of them, you can run all kinds of things, and we're going to go through that list here in just a second. Alright, so the cyclotron wave converter. You can take the cyclotron wave converter. This system right here consists of a DC motor and an AC generator. This is the AC generator side. This is the DC motor side. So you can take the output from the cyclotron wave converter, hook it up to the DC motor, and output AC 60 cycle into your house or into a number of houses. And of course, the bigger the AC generator is, the more houses you can drive. Now, compared to a nuclear power plant, this nuclear system is a lot more efficient. Again, nuclear power plants don't have these are highly efficient generator. This is a highly efficient motor. This is a highly efficient generator. Nuclear power plants would have a gas turbine, have a steam turbine in place of this generator running the AC generator. The steam turbine would hook to the AC generator and produce the power. So this is the way a nuclear power plant system works. But in the case of a nuclear magnetron system, the nuclear accelerated generating system, you can hook the DC output out of the cyclotron wave converter to the motor to get the AC out of the generator. All right. The government wants you to buy electric cars. How would you like to have an electric car that you didn't have to fill up or stop at a gas station your entire life, or the car's entire life? The nuclear accelerated generator system has a half-life of 28 years. That means you could have a car that would run without ever having to be refueled for 28 years. You can take the output of the cyclotron wave converter and hook it to these DC motors that you see in the middle of the picture here. These nice little blue things are DC motors. You don't have to have a giant battery pack because the cyclotron wave converter and the nuclear magnetron will continuously put out power, and any leftover power that's not going to your car can be fed through a AC converter and fed back into the electric lines. So, can we have nuclear cars? Well, sure we can. We don't need to have giant cooling ponds with highly efficient nuclear devices that can run electric motors. We have the proof. And we have cars that are demanding. We don't have to have any gas engines charging up batteries. We can do it with nuclear fuel. Here we have an electrical aircraft engine that the aircraft industry wants to run with DC power or some form of switch DC power. And the nuclear accelerated generator system can run an aircraft engine. There's no reason to have massive amounts of battery weight in an aircraft when you can have a lightweight nuclear aircraft system, your power system, and you've got a nuclear system. Not only is it lightweight, but it doesn't have to be refueled for 28 years. That you can actually have a power system that runs 28 years, can run an aircraft 28 years without having to be refueled. And I know a lot of you out there are going to go, it can't be. You just can't store that much power. Nuclear systems, the energy from nuclear systems is not finite the way gasoline is, that it just sucks it up. Nuclear, once you get nuclear isotopes emitting their particles, they have a finite life, but in some cases that finite life can be millions of years. In other cases it can be picoseconds, and some of the isotopes that we actually use can be anywhere from 3 years to almost 200 years, depending on what isotope you choose to extract power from. Do all isotopes work? No. There's a select few that will work just fine. Strontium-90 has a 28-year half-life. In other words, at 28 years, it's lost half of its power. So you could easily fly an aircraft for over a year in the air over a year without ever having to land it or refuel it. So this is just an idea that people have a hard time grasping this, and they say, well, you know, nuclear is heavy. Nuclear doesn't have to be heavy. Nuclear can be lightweight too, if it's done right. Again, this is an ion thruster, and NASA needs a lightweight nuclear system with a lot of power to run this thruster. The nuclear accelerated generating system would be the ideal candidate to power this ion thruster that we could get to Mars in 30 days. Thank you for watching our video. Feel free to contact Origins Law for a free license if you want to experiment with a nuclear magnetron.